All right, I'm going to go through and derive a bunch of formulas, basically all of them in special relativity. And the reason is, well, there's already a bunch of videos out there that derive these, and those videos get the right formulas and everything, but they kind of suck in my opinion because they leave me, and most people I would wager, with very little intuition. So you get to the end of the video or the derivation, and if that derivation's relied on symmetry arguments or almost wholly geometric arguments, that might be the most efficient and elegant way to get a formula, but it leaves me with very little intuition, and so it's a black box. So for me, when I was learning special relativity, a lot of these formulas were just black boxes I'd plug in, crank the handle, a number would spit out, but I had very little intuition. So I'm going to do it a different way. We're going to derive these in a series of videos in a very physical way, in a way that tells a story, and that will leave you with hopefully as much intuition as it's given me. Now, when I look at these formulas, like the Lorentz transformations, I'm like, oh, hey, look at that little term that I met in that story. I remember why you're there, and I have some intuition about what answers might be. So hopefully you find these to be as helpful in gaining intuition that is precious. There's precious little intuition in relativity, so as much as you can gain, the better. Hopefully you find them as helpful as I've found them. So we'll start with time dilation, like everyone starts, and full disclosure, the time dilation derivations out there are great. They're actually wonderful. In fact, this is the prototype. This was the only damn equation I felt like I understood when I was learning special relativity, because it told a story. There was a person on a train. There was some light. The light did some stuff. We measured some things, bada bing, bada boom. We got time dilation. And then the other derivations got, they kind of went off the rails. I'm not trying to make train humor here, but they started using some weird, bunch of math, a wall of math, and I got to the end and I'm like, I don't really get it. I can use the formulas, but I didn't get it. So we're going to use this as a prototype. So those time dilation derivations out there, they're great. I don't mean to besmirch those videos. They're wonderful. In fact, those are the prototype, and I want to use that to derive the rest of this stuff. So, we'll start with this formula. We may as well do it. The later derivations are going to rely on this. And so we'll start at the get-go, we'll do it right, but those other videos on this are actually wonderful. So what does time dilation mean? This is the idea that moving clocks run slow. I'll be more specific. Moving clocks that are moving with a certain velocity relative to an observer are measured by that observer to be running slow. What do I mean by running slow? Sometimes people say moving clocks move slow. It's like, no. A moving clock moves fast. That's what it means to be a moving clock. This clock on this red train here is moving really fast. Let's say half the speed of light. The clock's moving really fast, but it will be seen to be ticking slowly. So I'm going to give you the punchline here. The punchline is that moving clocks run slow. The rate at which this second hand is seen to move around in the circle by this person out here, this person can be like, damn, your clock's running slow. You got to put some batteries in that thing. It's going to be moving slowly. Or if you imagine that this person in the red reference frame had a digital clock and it just had a readout of 0, 0, 1 seconds, then 0, 0, 2 seconds, and it was just reading, time the way it should. If you're measuring from this black reference frame that's, say, at rest relative to the Earth, you'd measure this red clock that's moving very fast, but you'd see it read 0, 0, 1, and then wait. Now 0, 0, 2. You'd be like, dang, it took a long time to go from 1 second to 2 seconds. Your clock, again, running slow. That's what we mean. Moving clocks run slow. So why and what does that mean, and by exactly how much? So that's what we're going to derive in this video. And we're going to derive it the same way that all these things are basically derived. The starting point is the same starting point. It's that the speed of light is measured to be the same value by all observers. Now, that's a fact I can't derive for you. In fact, I know of no reason our universe logically had to be that way. You can imagine universes. I can imagine logically consistent universes where that's not the case. So this isn't something I could derive. This is an empirical fact. Michelson and Morley measured, some experiments back 100 years ago, and they found out that everybody measures the exact same speed of light. The speed of light is represented with the letter C. So C is a special letter. It's a special speed. It's the speed of light. And everybody in the universe measures this to be the same. That is to say, the ratio of how far light moved to how long it took to move by that amount move that distance is measured to be the exact same ratio by everyone, no matter what reference frame they're in, and no matter how like the motion of the source of light was. So whether that flashlight was flying toward you or away from you, whether the star that emitted this light was moving toward you or away from you, everyone measures the exact same ratio, and that ratio is big. It's 300,000,000. It's 300 million meters per second. It's actually like 299 million, but whatever. So 3 times 10 to the 8th meters per second, 300 million meters per second. Everybody, no matter how they're moving and no matter how the source is moving, measures the exact same speed of light. So this is the same for all observers. Again, I can't derive that. I mean, I could derive that if I hold some other thing to a first principle, but like, you could say, then I'm just kicking the can down the road. You could be like, why that thing? Well, I don't know. Again, we don't know any logical reason why this had to be the case, but it is the case as far as we can tell for our universe. And it might seem innocent enough. It's like, okay, so everyone measures the same speed of light. So what? Well, I'll show you so what. It kind of ruins everything. Everything gets blown up. You hold this still, something's got to budge, and that means basically everything else has to budge. So, all right, let's look at this example. So the way most people derive this time dilation formula is with, imagine a person's on a train. I love this derivation. I was like, yeah, love the train. Red person's on a train, and they take the cool green laser, the cool one. They shine that green laser up, hits the mirror, comes back down, and that's going to be, the path, the events. The two events are laser gets shown, and you can know that because this person will click the button. And then the light comes back down and it hits the ground. Maybe there's a little photoreceptor there. So as soon as that happens, flash goes off, or, some sort of tactile switch gets flipped. Who knows? Some way to measure how long it took the light to go up and then come back down. Well, here's the problem. If everyone measures the exact same speed of light, imagine what the person on the train sees. They see the light go right up and then back down. But the person outside, standing on the ground, at rest relative to the earth as this train moves by, isn't going to see the light move straight up and straight down. They have to see the light move to the right. Because if the light moved straight up, this train would pass it by, and now the light would not be in the train. So if you had some, if you're on an airplane and you just throw your keys up, those keys go up, they come back down, everything feels cool. If you're watching from the outside, these keys would trace this enormous arc through the air. They got to stay with you with the train. Everything in this train is moving to the right. The light, the person, clocks, the mirror. So from the train's perspective, light goes up, comes back down. But from your perspective, say out here on the ground, you see the light travel rightward up at a diagonal and then travel down rightward at a diagonal. Because everything on this train is also moving to the right. I mean, and if it didn't, it'd just be bursting out the back of the train, and that's not what happens. You can go try this if you want. So here's the fundamental problem. In fact, we don't even need much of a derivation here. If we're saying, if Michelson-Morley says that everyone, person on the train and me on the ground, are going to measure the same speed of light, well, look at this distance. Like, what distance did the person on the train see the light go? The light went up, back down. Let's say the height of the train is h. So the distance for the person on the train is 2 times h. Well, that's not the distance the person on the ground measures. The person on the ground, like, this is a triangle. So d squared plus h squared is going to be this diagonal squared. So this side here, this diagonal here, is going to be the root of d squared plus h squared. In fact, you got to multiply this by 2. So it went up, then came back down. So the total distance the person on the ground measures, we'll color code this. Distance measured by the person on the train, we'll use red for the person on the train, is 2h. Distance measured by the person on the ground is going to be 2 times the root of d squared plus h squared, because person on the ground sees it goes this diagonal, then the light goes that diagonal. The total length of the path it took for the light to go up and then back down would be 2 times the diagonal, and the diagonal from Pythagorean theorem is just the root of a squared plus b squared. So look at this, is bigger than 2h. It's got to be, because imagine d was 0. You'd get the root of h squared, that's just h. Then it'd be 2h, but we're adding to that. This diagonal's got to be bigger than h. So 2 of those diagonals has to be bigger than 2h. And so we'll look at this formula. If the speed of light is d over delta t, if the person on the ground is measuring a larger distance traveled by the light, and we're getting the exact same ratio, that means they being the person on the ground, have to be measuring a larger amount of time to have elapsed between the light getting shown initially and the light hitting the ground. So it really is that simple. If all you wanted was, hey, why do moving clocks run slow? Or to put it another way, why do not moving clocks run fast? It's just this fact, like no real math needed. If the person outside sees the light traveling farther, and that ratio's got to be the same, like as was determined by Michelson and Morley, then that person outside's also got to have a larger denominator. So larger numerator divided by larger denominator gives you the same ratio as the person on the train would have a small numerator and a small denominator, and that gives you the same ratio. So that's the only way it could be. If you hold this C still, something's got to budge, and it's this time. No one expected this. Everyone thought everyone measured the same amount of time. But if that were the case, someone outside would measure light to travel farther. Over the same amount of time, they'd be measuring a larger speed of light. This is what Michelson and Morley thought. They were like, oh, surely if we go measure the speed of light, some people are going to measure it faster, but that's not what happened. Everyone measured the same speed of light. That means time has to budge. And all we're going to do now is derive by how much does that moving clock run slower than the clock held by this person out here. So let's do that. So speed of light as measured by the person on the train. Speed of light by person on the train is going to be distance per time. So the total distance is 2h. So it went up, then it came back down, divided by the time that was measured by the person on the train. It's important. We've got to use their clock. The time measured by the person on the train. I'm going to represent that with red delta t. Some people put prime here. I don't like that. That gets in the way of all the squares and everything. I've got color code, so that's how I'm going to get away with not writing the prime. Or you could imagine writing this as T for like train. So this person's got their own clock, And so they're going to take 2 times h divided by the time they measured for the light to go up and down. That's their speed of light. Well, the speed of light the person on the ground is going to measure is going to be speed of light is this total distance here, which is 2 root, it's going to be 2 root of d squared plus h squared, and then divided by the time that the person on the ground measured. This is the total time it took. Total time it took to go up and then back down as measured by the person on the ground. And we're saying these ratios are the same. So I just want to know, okay, by how much are these times different? So to do that, to get a nice clean formula, I want to get rid of these h's and want to get rid of these d's. I can get rid of the h pretty easy because this is the same height. We're looking at the same train, so same height. Yes, there'll be some length contraction in the direction of motion, but there's no contraction perpendicular to the direction of motion. So we're going to solve for this h over here. The train will look to be the same height to the person outside the train as it seems to be for the person in the train. It won't seem to be the same length, more on that later because that length is in the direction of motion. But if we solve this for h, we're going to get that h equals c red delta t, time measured by the person on the train, divided by 2. And I'm going to take that and I'm going to plug it into this h right there to get rid of h. So I'm going to take this whole quantity for h and I'm going to plug it in over here. And I want to get rid of this d. And so how do we get rid of the d? Well, we're presuming the train's moving at a speed v. So, distance is rate times time. But the total distance the train moved was 2d. Remember, I'm writing this d as one side of this triangle. But the light went up, then down. So what I'm calling capital D is actually half the path the train took forward. The light took this diagonal path. The train just went forward. So I just want to know how much forward the train went. It went 2 times d forward in the amount of time delta tg. And speed of the train's that. The time it took for the light to go up and down was delta tg. So this is how far the train went forward. 2 d's in a time. Speed of train, not speed of light. Your train not going the speed of light. Speed of the train times the time it took for the light to go up and down. That's how far the train moved forward during that time the light moved up and down. And we can solve this for d. We get that d is v delta tg over 2. And this is what I'm going to plug in for d. I'm going to take this formula, plug it into here for d. So let's do that. First, I'm going to clean this up a little bit. I'm going to move the delta t over and divide by the 2. So it's not such a mess over here. So we get c delta tg over 2 on the left equals, and then we get the root of d squared. Well, that's just this squared. So it's v squared delta tg squared over 2 squared, which is 4, plus h squared, and h is what we got over here. So this is h. So we get plus c squared delta t as measured by the person on the train squared. We could put train here to remind us it's measured by the person on the train, divided by 2 squared, because we're squaring this whole term, h squared, and we get 4. All right, so we're almost there. We just got to square both sides to get rid of this root, and we're going to get c squared delta t g squared over 4 is going to equal, I'll just copy this and move it down here, this whole mess in here. So copy, paste, you come down there. All right, there we go. What do we do now? I'm going to erase that. We can divide by or multiply by 4 and get rid of all those 4s. So multiply everything by 4, get rid of these like that. And now we can combine TGs. So I'm going to move this TG over here and pull out a like factor of TG. Sorry, of TG squared. So we get TG squared times the quantity c squared minus v squared. So, you know, when I move this over, I'm going to get c squared, tg squared minus v squared, tg squared. But if I pull out a common factor of tg squared, I'd get c squared minus v squared equals, you're left with c squared delta t, you know, measured by the person on the train, squared. So finally we can divide by c squared, and we would get that delta t as measured by the train squared equals, so if we divide both sides by c squared here, you're going to get 1 minus v squared over c squared, and then times delta t g squared. Finally, we could take a square root, and we get the answer we were looking for. The amount of time that elapses as measured by a person on the train is going to equal the square root of 1 minus v squared over c squared multiplied by, we took a square root, so this becomes just delta tg, multiplied by the time it took the light to go up and down as measured by a person on the ground. This is the time dilation formula. This says that moving clocks run slow. Why is that? Well, this is the time measured, this is the time measured by the moving clock. Red is the time measured by the moving clock. And look at what you get. The moving clock is going to measure amount of time equal to this factor times the time measured on the ground, but this factor is less than 1. Look at, you have root of 1 minus something. Well, this thing's always going to be positive here. You got v. You might be like, what if it goes left? Well, you're squaring it. It doesn't matter. V squared over c squared is a positive number, or 0 if the v is 0, but it's never going to be negative. So this quantity in here has to be 1 or less. Well, that means the root of that is 1 or less. So the moving clock will read less time. It measures some fraction of the time measured by the person on the ground. In other words, my clock out here might tick off like, hey, 8 seconds went by. What would 8 be? 12, 8, right there. 8 seconds went by. Maybe your clock is like, oh, no, buddy. No, only like 7 seconds went by. So it wouldn't tick through as much time. Moving clocks run slow. This is the time dilation formula. And this is going to be important for every other derivation we do in here. That's the derivation. Again, to recap, it's fundamentally just based on the idea that a moving reference frame, you can see light move farther in that reference frame, but that means you have to measure more time taking place if the ratio of distance per time is going to be the same. So, you know, logically speaking, that's really the only ingredient here. The details is all this math, and if you go through the math, you get the details, gives you this formula, which is the formula for time dilation. I'm going to make another video because if you're super clever, you might be like, hold on just a minute. This person on the train has just as good of a right to say that you on the ground are moving left. You know, they would see you moving, and you could justify, hey, I'm well within my right to claim that I am at rest in the train, because every inertial reference frame is just as good as any other. There's no better inertial reference frame. And so I can claim that you are moving leftward. That means, shouldn't I measure your clock to run slow? And that's true. Now, you're not going to like this. I didn't like it either. I was like, that's impossible. But it's true. The person in the red reference frame will measure the black clock run too slow, and the person in the black reference frame will measure the red clock to run too slow. Now, I know that sounds like a paradox. In fact, it's the germ of what's called the twin paradox. So I'll make another video. It turns out it's not a paradox. It is weird, admittedly. It feels like game over. It feels like special relativity is logically inconsistent. but it's not. All moving clocks will be seen to run slow. That means red person sees black frame run slow, and black frame sees red person's clock run slow. So this works either way. Again, I know it sounds inconsistent logically, but I'm going to make another video. So if you're interested in learning why that's not a paradox, watch the next video. I mean, one last thing, the speed of light's enormous. So the reason we don't notice this in everyday life is you're dividing by 300 million squared here. So unless your speed is enormous, this is going to effectively just be 1. So, the denominator here is c squared. That's 9 times 10 to the 16th. So unless your speed is fast, and I mean like, you can't be like, okay, I've got a Lamborghini, buddy. I'm going 150 miles an hour. I'm like, no. That's only like 80 meters per second. 80 squared is 6,400. That's like nothing. Sorry, buddy. 6,400 over 9 times 10 to the 16th, that's basically 0. Your calculator probably doesn't even have digits out to that point. So this is going to return 1. So at normal human speeds, there's no measurable time distance or difference. Now, they have done this with atomic clocks. If you do this with atomic clocks, you synchronize 2 atomic clocks, then you put one on a plane, fly it around the Earth as fast as you can, you bring it back, it's off. It's off by how much? Just the amount special relativity said it should be off. There's other experiments that have been done after that. That one was a little sketchy. It was early on. Technology's gotten better. We've been able to test this better and better and better, and it works. Empirically, this is the correct formula for how moving clocks will age relative to each other.